This lab is on classification again. It sort of builds on what we did last time and shows you some very practical things that you need to keep in mind when you're doing classification with scikit-learn. So as usual, we have our incantation at the beginning to get things working. And we've added these optimize and do classify functions, which we talked about a little bit in the last lab. I'll just very quickly go over these again. Do classify is this workhorse we're using to do classification. We basically have a data frame which comes in, the in data frame over here. And from that in data frame, we basically get a bunch of features, a bunch of column names. And we're basically going to get a sub-data frame from that in data frame over there. And we're just going to take the values of it, and that gets us the features in the samples times features matrix form that scikit-learn wants you to have things in directly. And we get the target basically by looking at the target name. If you look up here, there's a target name and a target one val in the argument list over here. And the target name is just basically the name of the column which you want to use as the column for the ones and zeros, or the trues and falses, or the males and females, or whatever you're doing for the classification. And the target one val is basically the value you want to, in that particular column, that you want to have as a 1. So for example, if you're talking about males and females, you would say gender is equal to male if you wanted that to be a 1. There's a mask which goes in here, and that's basically a mask which tells you which one is your training set and which one is your test set. It's just basically a Boolean mask. We'll see how it's used in a second. And you can always use this reuse split dictionary, which we'll come to later as well. And the reuse split dictionary is once you've already split stuff and you want to test different classifiers on the same test set, that's what you'll use for that. And then there's a score function which you can pass into this as well. And the score function is something that you don't have to deal with right now, but we'll talk about a little bit at the end of today. Because in a cross-validation fold, you can use a different score function than the typical accuracy that the classifier uses. And then finally, it's the number of folds. And in general, we're going to use 5-fold cross-validation. And there's still one more argument out there, which is the number of jobs. Scikit-learn gives you the ability to parallelize your cross-validation. I've had some problems on my Mac using njobs more than one with some threading bug in MKL in the BLAST library. If you're on a newer version of the newer Mac or so on and so forth, you may not have this problem. So you may actually be able to speed up your code by putting njobs equal to something else. So I'll leave that to you to experiment with. OK. So what we're doing is if we have a mask, basically we use the mask to get the training and test sets from the x and the y's, essentially. If we have a split dictionary which with keys xtrain, xtest, ytrain, and ytest, we just use that instead. And so that's just these two different ifs over there. And then if we have the second argument here, which is a parameters dictionary, which is the form of the dictionary that the cross-validator, the grid search CV in scikit-learn uses, we can pass that in as well. And we just use the CV optimize, which we defined a little bit above, to actually do the optimization there. And then once we've optimized it, we by doing cross-validation. Remember, in cross-validation, we're splitting stuff into training and validation folds. We're going to actually fit on the entire training set again. That's what we're doing over here. And then we're going to get the training accuracy, which is the accuracy on the set that it was trained on itself, and the test accuracy, and then print those out. Also print out the confusion matrix and return the classifier and basically the training set and test set. The CV optimize up here basically is really simple. It just takes your original classifier. It takes as param grid the parameters dictionary from here and does a grid search on it. And it fits the grid search on your data. And remember, from here, what goes into here is the training set, the training response. It prints out the best params, the best score, and the grid scores to see, so you can see how your performance varied. And it basically returns the best the best model that was found by the cross-validation process. OK. So in a sense, I wanted to go over these functions because it gives you an idea of what the entire process is. With that in mind, let's just go ahead and do some of this. These functions are basically to plot the points on a classification graph and to plot the probabilities. I'm not going to go into that in any detail. And so here I'm again reading this heights weights data. am reading it. I don't know if I've ever shown this before, but you can read CSV files and pandas from URLs. Quite useful. And I'm just looking at the shape of this. And basically, I'm just going to sample it down to 500 points from 10,000 because I want the diagram to be sort of clear. You don't need to do that, but I just wanted the diagram to be clear in this lab. And I'm seeing roughly, I just wanted to check that the male-female gender balance wasn't totally whack. So I just checked to see that that's about 255, which is about half of 500 in this. So again, we're going to split this data into training and test sets. We use train test split from scikit-learn.cross-validation. And basically what I'm doing is I'm actually just taking the sort of number of things I have. I'm just taking the indices. And I'm taking these indices and randomly splitting some of the indices into the training set and some of the indices into the test set. And then what I'm going to do is I'm going to create this mask, which is of the size of the entire thing. And it's just set to a bunch of ones. And for whatever indices that are in the training set, I set them to 0. Whatever's in the test set, I set it to 1. And whatever's in the test set, I set it to 0, basically. And you can see what it looks like. So it's going to be a bunch of trues and falses, which I can now use to index my X matrix and my Y vector. OK. So we're going to do logistic regression. We're going to do a regularized logistic regression. The default in scikit-learn is to do this as an L2 regularized logistic regression, i.e. with a squared loss. You can see the parameters for it here. I just took a whole bunch of sort of like, this is typically what you do in these hyperparameters. You take sort of power law, I guess, exponential steps. So that's 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0, and so on and so forth. And I just do this do classify with this logistic regression classifier that I instantiated, passing it the parameters and the data frame. And I plot what the results of this look like. It turns out that c equals 0.1 is the best value of the hyperparameter. And here's all that output of all the parameter sets. There's the accuracy in the training data is 0.93, 0.94. It looks like cross-validation took care of making sure that we don't have any overfitting. That's what the confusion matrix looks like. And we'll come to the confusion matrix in a second. But here's a graph of the classification and the classification regions, by which I mean that, again, it's not terribly clear over here, but you'll be able to see it in the notebook, that this region is blue and this region is red. So any sample which would have been, for example, here would have been classified as red, and any sample there would have been classified as blue. OK. So here are some functions that you will be using again and again. These are part of the scikit-learn API, and so you should kind of get familiar with them. Predict is one of these functions. And what predict does is that it basically looks at the probabilities, and I'll come to that in a second, of the prediction on the test set here. I've passed X test in. And if the probability is greater than 0.5 that this particular sample was a 1, I'm going to call it a 1. That's what predict does. That's all. These probabilities themselves can be accessed in classifiers which have probabilities. SVM is a classifier which does not give you probabilities, for example. And you can sort of access it like this. So this is the classifier.predictproba, which is just the probabilities. The first column here, and I'll go up a little bit. It's actually really not a column. It's a bunch of rows. But it looks like a column, so I'm going to sort of like pretend it is. These are the probabilities of having zeros, and these are the probabilities of having ones. Really what it is that for each sample, it gives you the probability that this was a 0 and the probability that it was a 1 over there. And you can access, obviously, one has to be 1 minus the other. And you can access these by sort of doing something like, I think I managed to eat up a particular cell. So I'll just open up a cell here and add that in. So these are the probabilities of getting the ones. That's because that's giving you the second probability from each one of these. And that's the probability that the first sample was a 1, that the second sample was a 1, and so on and so forth. And you can plot these if you like. After all, it's just a vector. So plotting it is really simple. And this is one of these telltale plots you'll often see, in which you have a lot of the samples have probability 0 of being male over here, because they're well inside, if you like, the female region of this plot. So those are the ones, if you go look at this plot, which are here. sort of well inside the female region. And then you have well inside the male region. And you've got those, and then you have a bunch of those who are in between at the boundaries. Okay, we can plot the probability contours of this as well. And you can see that these contours are rather tight. So you're going from like 0.2 to 0.9 in really, really fast, in a fast amount of time. And notice that logistic regression is basically what's called a discriminative classifier. It basically gives you a boundary between these two things. It does not try and model each, what you could think that, oh, these are heights and weights of males and females. Yeah, we kind of expect that the heights and weights of males and females are going to be two separate Gaussians. So I can model this as one Gaussian, I can model that as another Gaussian, and sort of do this classification based on finding two Gaussians. That's what's called a generative model. We'll talk about this right at the end of the semester. This is a discriminative model where you actually try and just find a boundary between these two different things. So that's sort of the probability contours for logistic regression. Here's another function which is there in the scikit-learn API. It's the score function. And it's used to evaluate parameter settings in the cross-validation loop. So whenever you're doing the cross-validation loop, you're actually looking at the score function here. And I'll come back to this in a little bit. But the thing you need to take away right now is that for classification, basically the default is the accuracy score. So it's just looking at the accuracy, which is the number of samples that were classified correctly. And so what it's doing in the cross-validation loop is it's saying, okay, in this fold it's so much, 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 on average it's that much. And then it's going over all the different values of C and saying which of these averages is bigger than the others. But it's the averages of the accuracies, and that's kind of important to remember. Okay, so for some applications, other scoring functions are better suited. For example, in unbalanced classification, the accuracy score is often uninformative. So we can pass other scores to grid search CV, and that's why we had that little score func argument. And I'll very briefly allude to this at the end of this lab, and probably have sort of like some more information somewhat later in the semester on this. Okay, so boom, the score is actually calculating the accuracy score and telling me it's 0.916 over here. Okay, so that's logistic regression. Let's actually do an SVM instead on exactly the same data set. You can do this using linear SVC, or you can do this using SVC. There are two different implementations of SVM in the scikit-learn package. The linear SVC is much faster if you're doing a linear SVM, and by linear I mean you're looking for line boundaries. This is the one you do want to use if you want to use anything which is using the kernel trick. So if you want to use the RBF kernel or a quadratic kernel or any one of these kernels, then you do need to use this one. So just keep that in mind. It's kind of important actually on the homework, the very last part of the homework. So again, I'm going to set a bunch of parameters, and the way C is defined over here, I'll talk about that a little bit at the end, but it's essentially defined in complete sort of analogy to the logistic regression. And it's typically, if you like, it's 1 over lambda, both in logistic regression and in sklearn, if you look at the corresponding log losses and the hinge losses, which we'll again look at right at the end. So I'm going to do exactly the same thing. So now you see why we put in all this effort to make this kind of machinery to do this do classify function, because I'm just going to instantiate a instance of the SVM classifier here, and I'm just going to pass it in. I'm going to pass in that parameter grid of the C's. Linear SVMs have no other parameter. If you remember, there's a gamma parameter in the RBF kernels, but there's no other parameter for the linear SVMs. And it's exactly everything else is the same. I'm passing in height and weight, the data frame DF. I'm looking for the gender male to be 1, and I'm just going to put in that mask. And I'm doing exactly the same thing I did before. I'll look at this, and I get this structure over here. And it's pretty much the same line. It's not terribly different. That's not that particularly surprising that it's not. But there is no predict proba, because how the SVMs do classification is that they don't actually give you any probabilities. They look at this sort of like distance from the middle of the margin, that line, and use those to make the differences. And so you use a function, and for all such classifiers in sklearn, you don't have predict proba, but you have a decision function instead. And the slight difference from predict proba and decision function is that you just basically get a vector in decision function, where in predict proba you had the probabilities of 0 and the probabilities of 1. Even though you didn't need both of them because they had to add to 1. Of course, you do need them if there's, if you're doing multi-class classification, which we are not going to talk about. So there's your decision functions, and you can do exactly the same thing. We're going to plot the decision functions. Here's basically a histogram of those distances, and it's telling you that the way the SVM does things is slightly different. It's not like you have those histograms large over here and here. They're somewhat large in the middle where most of those samples lie. So it's really actually telling you what the distances are. That far away samples are a little bit far away. It's not like in probabilities those things got stretched to be like that. Instead, this is just using distance. So that's why it looks like that. And you can actually see that when you plot the distances themselves. So that's the 0. That's where the line is. And that's a line of 12, and that's a line of -6 and -12. So there should be a line of 6, which is kind of, here it is. It's not particularly clean on this screen, but you can see it in the notebook. OK. So this next little piece of code I stole from Jake Wenderplas's notebooks at the European Astronomy Conference, this little piece of code. And I would actually encourage people to look at anything that Jake Wenderplas has written, because he's an incredibly good writer. And all of his stuff is up on GitHub, and there's incredibly good tutorials for machine learning and so on and so forth. And actually, one of these I've put in the resources section of our website, which is a new tutorial on doing statistics with resampling, rather than getting hurt in the head with all the t-tests and all of those kind of things. Absolutely great person to follow in terms of learning stuff. So he wrote this little function there, and which allows us to actually plot this decision boundary very clearly, including the margin that we've been seeing in the lectures. And you can see what all the support vectors that were picked out were by this little cover thingy. Also, do check out on beta.o'reilly.com, again, Jake Wenderplas's SVM tutorial. The tutorial actually has an interactive explanation of how SVM vectors are created. The support vectors are created. OK, so here's 2 separate classifiers. They're both linear classifiers. One works by probabilities, and one works by distances. And this is how you do them. So this should help you in your homework and your projects and everything. Let's move on to sort of an important concept. If you looked at the output of any of these classifiers, we were always outputting something called a confusion matrix. And a confusion matrix basically is telling us how many things of a particular type are predicted to be of a particular type. So the upper left corner basically is basically the true negatives, and the bottom right corner is the false positives. In other books, you'll see this handled in different ways, but that's how sklearn basically pops it out for you. So I'm just going to stick to the sklearn convention. And keep this in mind. This is like 84 there, 101, and there's 7 and 8 on the diagonals. Let's go look at this little figure here. So in the upper left corner, it shows you the true negatives. In the bottom right corner, it shows you the true positives. Oh, I've copied it back down here so that you can look at it. So what this is saying is that 103 in the test set, we know what the things are in the test set, right? So we can play this again. That 103 of the positives in the test set were classified as positives. The true negatives, very conveniently hidden by my pointer, 84 of the true negatives are being classified as being predicted to be negative. But there are a bunch, not too many, but there are a bunch of false positives and false negatives. The false positives, that's the upper right corner of this matrix, is basically saying that 8 of these were actually negatives here, in this case females, but they were classified as males. And 5 of these were males, were classified as females. So those are the false negatives. The confusion matrix is kind of important to see. The first thing it does tell you is that, look, 103 plus 84, 191 of these things were classified correctly. And you only had this wrong, these things which are on the diagonals wrong. But it also becomes important when you're looking at asymmetric classification. There are in some cases where false positives are more expensive than false negatives, and false negatives are more expensive than false positives. We'll come to that in the sort of companion lab to this, as well as maybe a little bit later here. So there are a bunch of metrics that you can calculate from these. The true positive rate, or the recall, the false positive rate, the precision, and the F1 score, which is a combination of recall and precision. I won't go over these in any big detail, except to show you that there's a classification report, which basically is provided by sklearn in sklearn.metrics, and it actually gives you all these numbers for this data set. One thing I do want to point out, however, is that the true positive rate and the false positive rate are interesting in that if you look at the true positive rate, it's the true positives divided by the true positives plus false negatives. If you look at the true positives plus false negatives, they're here, along this sort of like line over here of all observed positives. So basically, it's the true positives divided by the observed positives. The false positive rate, on the other hand, is the false positives divided by the false positives plus true negatives. False positives divided by false positives plus true negatives, or false positives divided by observed negatives. So the true positive rate, which is in something we'll come back to in the ROC curves in a little bit, they only concern themselves with one column here. And the false positive rate only concerns itself with one column here. So in this data set, I have about 255 males and 245 females. But I might have a data set, for example, a data set in a fraud situation where maybe only like 20 people committed fraud out of 1,000, where this is extremely skewed. However, the true positive rate and the false positive rate don't care about this skew. They're just coming from one of these rows over here instead. So that makes it actually kind of useful to plot the true positive rate against the false positive rate in an ROC curve, because it says nothing to me about the, in other words, it's not confused with how many of the positives were there and how many of the negatives were there. It's clean of that, and I need to put in that information myself separately. So that's one advantage of looking at these things. Precision and recall, on the other hand, actually, so to be very precise, recall is basically the same thing as a true positive rate, so that goes over here. But precision, on the other hand, is actually going as the true positives over true positives divided by false positives. So that's basically the ratio on the predicted positives. And so that actually goes across those and gets affected by the balance. That can be an advantage or a disadvantage depending upon what you're doing. Anyway, why do we care about all of this? We'll come to this in a second. So think about the situation. You're a cancer doctor, and you're looking at people's mammograms. And based on the features on these mammograms, the brightness and all kinds of things, you're trying to predict whether a given patient has breast cancer or not. Now, there's not too many people have breast cancer, all said and done. I mean, there are people do have breast cancer, but it's a smaller fraction of the female population. So this is one of those situations where, number one, you have an extremely asymmetric data set. That you will have some mammograms in which there is breast cancer and a lot of mammograms in which there isn't. The second problem with this is that if you made a classifier based on these photographs and put a threshold of 0.5, that anybody who had a greater than 0.5 possibility of having cancer as somebody that you needed to follow up, you would end up killing people. So it's really, really sort of important to understand out here that false negatives in this particular situation are incredibly painful for you. Because what's happening with false negatives over here is that here is a person who has cancer, and let's say the probability of having cancer was 0.4, and so you said, oh, based on my 0.5 threshold, this person does not have cancer. And you say, okay, well, you don't have to do a biopsy, and you might have just condemned them to death. So in this particular situation, you want to be extremely conservative, and part of being extremely conservative over here is saying that, well, okay, well, I'm going to change my threshold. Anybody who has greater than 5% chance of having cancer, I'm going to classify as has cancer. So your threshold then is not 0.5, but it becomes 0.05. And you say anybody who's got more than 0.05 has cancer. At the very least, go to a doctor or do something with that person. So this is a situation where the cost of a false negative is much higher than the cost of a false positive. What's a false positive? In this situation, a false positive is a person who does not have cancer, but whom you told, hey, you got cancer, go get a biopsy. Yeah, there's going to be a certain amount of mental anguish, at having to do a biopsy, but you know, in the end of the day, it's not the end of the world if a person has to do a biopsy based on a false positive. But it is the end of the world, literally, based on a false negative. So it's kind of important, these thresholds in these predictions in some of these fields. Okay, so how do we deal with this particular situation? There are two ways to do this. One way is to basically build this in directly into the into your cross-validation loop. We'll talk about that. Actually, we probably won't talk about that today. We'll talk about that a little bit later. The other way to do it is to actually create what's called an RSE curve. So with the RSE curve, what we're doing is the following. If you remember, when we just did the accuracy score, that basically was your kind of intuitive notion that anybody who you know, any sample which has a greater than 0.5 probability of being positive, we're going to call positive. But I just told you what we can do is we can actually change this threshold quite arbitrarily, right? I can make the threshold 0.99. Only anything which has a probability greater than 0.99 of being positive is going to be a positive. I might get one sample because, you know, these probabilities are on that graph which you saw earlier, which looked like that kind of boat. I'll probably get more than one sample, but I'm really putting the bar really high. Okay. So when you do something of that sort, you've created one classifier which has this threshold. As I change this threshold, what I can do is it's 0.99 now. I'm going to make it 0.95, and I make it 0.95. I'm going to get more. I'm going to get more and more positives come up, right? Because at 0.95, there might be 5 or 6 of them. Then I'll go down to 0.9, get 10 of them, and so on and so forth, and so on and so forth until I get to 0. And the moment I get to 0, I'm classifying everything as positive. So I'll get everything as positive then. And that's what you do in an RRC curve. Is basically what you do is actually something very similar to this. You don't actually go down the thresholds, but you simply say, okay, let me assume everything is positive. Now, let me start moving things. Sorry, I said that wrong. Let me assume everything is negative. Now let me make the first thing positive. And the thing I'll make positive is the one that has the highest probability. I'll sort everything by probabilities. In an SVM where I don't have probabilities, I'll sort everything by the value of the decision function, from highest to lowest. So I'll say, here's the first one. Okay, so that's going to be a positive. Now, that is so goddamn likely to be positive that it's going to be a true positive. And so that's going to increase my true positives first. Okay? So that's what happens over here. It increases my true positives first. Actually, I should probably show the other diagram because that makes this much, much more clear. So what I'm doing is I'm moving up this list where the probability was 0.99. And here I get a classifier, as you can see. In this book, the true positives are kind of up here. And everything was negative to start with, and then you suddenly got one move up to become a true positive because it was 0.99. It's so goddamn high, this probability, that it's got to be a true positive. And then you keep moving, and you're going to get some more true positives. And then the first one you get at some point, that was a false positive, and you have a 1 show up over here. And so what happens is that you have this kind of stepped-up diagram where you go up like this, basically. And this, by the way, is the plot of false positive rate over here against true positive rate. False positive rate hasn't shifted. True positive, and so the true positive rate goes up, and false positive, true, false, and so on and so forth. You'll get the step function thing, which is going all the way. And that gives you this kind of RSE curve, which is basically just sort of interpolating those points and joining them. But the process should be reasonably clear to you. What we're doing is that we are setting these different thresholds, 0.99, 0.98, 0.97, 0.96. Based on these thresholds, we're calculating the scores, the accuracies. And based on based on that, we're plotting a point on this RSE graph of the true positive rate and the false positive rate. That's all there is to it. There's nothing more. Okay. Again, here's the confusion matrix. Again, remember the true positive rate was basically the true positives divided by the observed positives and the false positives divided by the observed negatives. And we go ahead and we plot this. And here's a little bit of code to do it. What it actually does for you is that it sets up the graph and everything for you. And in this case, it uses the predicted probability. In this case, it uses the decision function if you have a probability. It uses the built-in sklearn function RSE curve. And what RSE curve is that it does is that it basically takes the actual test values, and it tells you the predicted probability values, and it does this whole thresholding for you. So you don't even have to do it in scikit-learn. I explained to you how you can generate an RSE curve, but scikit-learn actually generates this for you. And what it pops out for you are the various thresholds corresponding to those movements that I just showed you of, moving one sample over from being negative to positive, and gives you the false positive rate, true positive rate, and the threshold of that one, and then it keeps doing that, and it gives you an entire list of false positive rates, true positive rates, and thresholds. And it also calculates the AUC for you over here, this function. And the AUC is basically the area under this curve, under this RSC curve. Remember that the false positive rate and true positive rates have to be constrained to be between 0 and 1, right? Because they're fractions. So the total possible area over here is 1. You can't get more than 1. So, from a very traditional perspective, where you want to sort of maximize your true positives and minimize your false positives, the best possible classifier would be here. We've, of course, seen that in the cancer, in the cancer situation. One of the things we might want to do is basically trade off false positives and false negatives. We don't want any false negatives. We don't want to tell people not to go and get biopsies, but we're okay with false positives. In such a scenario, we may be looking for a classifier here. So it's kind of important to understand what your domain is before you try and use an RSC curve kind of dumbly. And a lot of people will tell you, go to the northwest corner, go as far as possible towards there as you can go, and you say, okay, look here, and then you just killed a whole bunch of people. Not a good thing. Okay, so let's plot the RSC curves for our scenario here. And we can see what it looks like. This is the one for the logistic. This lab argument out here is basically a label. And it puts these little labels on this curve here for you, telling you what the thresholds were. Since this is a very balanced data set, equal number of males and females, you actually get what you sort of expect. So the probability of 0.5 is in the upper left corner over here. That's what we'd use. It doesn't make sense to just arbitrarily use a threshold of 0.08 to make this classification of males versus females over here. And so this is basically, it's kind of a stupid function that I just wrote. It's basically skipping every 10 off them and putting labels up. And similarly, this is what it looks like for the SVM. And I've called this logistic, which is clearly wrong. I shall fix that as my label. And it also tells you what the area is. It's 0.97 for this one. It's 0.97. They're basically comparable. And you can also see over here that it's like minus 0.13 to 0.4, and that sort of 0 comes roughly over here. And here you're actually plotting the decision function values, the distance, essentially, from the separating hyperplane. So that's sort of RSC curves. The very basic thing about RSC curves, how to interpret the RSC curves is sort of more there in the companion lab. But you should know how to make one. So I want to sort of talk a little bit about this notion of the score function we had in the do classify. There's a bit of a philosophical point here. What we did to produce these RSC curves is that we were basically looking at the test set. And in a sense, we're choosing models on a test set, which should actually worry you a little bit, in the sense that we basically trained the models on the training set. We kind of chose the best parameter C on the validation set. And we did this for a logistic regression. We did this for an SVM. Maybe we'll use a decision tree. Maybe we'll use naive Bayes. Maybe we'll use some other classifier. But there are these 5 different classifiers whose performance we are now starting to compare on the test set. And we're going to say, this one has the best performance, a maximization problem. So we're doing a maximization problem on the test set. And you know what happens when we do these maximization problems on any set. That set's verboten. You can't use that set anymore. That's generally OK in this situation because we're going to look at future. We're doing this classifier to work on future data. But you can't now make any other conclusions about it based on your test set, because you've kind of used up your test set, so to speak. There is a bigger problem if you try and do this thing. And actually, I believe there are companies out there which kind of do this for you and perhaps haven't entirely realized that this is a problem. That, OK, here's a classifier. And what I'm going to do is, yeah, the performance is not so good. Here's the next classifier I'm going to try. Yeah, performance is not so good. Here's the next classifier I'm going to try. Yeah, performance not so good. Here's the next one, and the next one, and the next one. And soon you've tried like 40, 50 different classifiers. The moment you've tried 40, 50 different classifiers, something should start bothering you, because there is the possibility that just randomly it is possible that one of these classifiers is going to do well. And so when you do this, you need to, they should remind you of things like multiple comparisons, and you should start thinking of, saying that a classifier is best requires a far, far greater degree of, thought in that situation than just saying, well, I'm just going to compare the different values. Because you may actually be choosing a classifier that has the best possible value, but which happened completely by random just because you compared so many of them. So when you're doing these auto C curves on the test set, you're doing exactly the same thing. You're saying, basically, I'm looking at a whole bunch of these classifiers, and I'm going to choose this one over here in the upper left corner. But I'm doing this on the test set, so now I can't touch the test set anymore. I'm done with that test set. So that's something you should keep in mind when you do this sort of thing. However, there is a way to sort of get over this, and this is to use that score function. So what many people will do when they have balanced sets like this is that they want a classifier which works kind of well, even if the sets are somewhat imbalanced. And we'll see soon that imbalance puts you here or puts you there and does things like that. And what they'll do is they'll take the area under the curve. And they'll actually calculate this area under the curve in each and every cross-validation fold. There's nothing that we did here which said that this could not have been calculated instead of the accuracy score in the cross-validation fold. So they'll actually calculate the AUC in the cross-validation fold, and they will choose a model based on maximizing the AUC. So in a sense, what they've done is they've sort of like combined the information of all these little classifiers into one number out there and said, oh, okay, this is going to be the model I'm going to choose. And having done that, they have not sort of used the test set. So that's not necessarily a bad thing to do. We won't actually do this in the homework. In the homework, we're going to have you compare stuff just for the sake of simplicity on the, on the test set. But it's something to keep in mind that the more you can get away with by doing the cross-validation process, it's not a bad thing to sort of do. Again, there is a problem with this, and the problem with this is that if your validation set is really small, and you have to fit C, and you have to figure out this whole AUC business, and you have to do other stuff, you're actually using very little data to do a lot of stuff. And you'll see that when you do this, your answers in your cross-validation folds are extremely different from each other. So the variance becomes very high if your validation is small. So it's one of these choices you got to make, depending upon the amount of data if you have. If you have a lot of data in your validation set, go and change your score function. Put something else in there. And it's not just an AUC you can put in. You can put in precision score or recall score, all of which are defined in sklearn for you. If you put in a precision score, it'll try and maximize precision for you. And so you can do this on the cross-validation set directly if you want. But we won't be doing that in this homework, so I'll shut up about that now. OK, so I'm going to actually switch over to the other notebook at this point, and in the next time we do this recording, we'll continue into that notebook as well. So here's the other notebook. Let's just maximize that. So this notebook now is really about the bread and butter of what's happening on this homework. It's basically a model comparison that we're going to talk about. So again, we have the standard stuff. It's the same functions that we had earlier set up here, but now we're going to actually look at a very interesting data set, and this is a data set from a telecom company of their customers. There are various features of the customers: which state they were from, their phone number, do they have an international plan, do they have voicemail. This is a slightly old data set. The day minutes they used, the amount of money they paid for the day, the evening minutes they used, and so on and so forth. And based on this, they also actually have this particular column out here which is called churn. And churn in these kind of situations is basically a marketing term which kind of says, will the customer leave us? So a churn is equal to true means that, oh, I'm AT&T, this customer is going to go join Verizon. So for AT&T, that customer is churned. So the idea behind this data set is to look at all these features and see if you can actually predict which customers are going to leave you. And based on which customers are going to leave you, you're going to sort of offer them something so that they don't leave you. Why is this an important thing to do? Think about it. If you have a $40 or $50 bill every month, that's $600 over, basically a year, and that's $2,000 over 2 years that company tends to lose and doesn't want to. So they want to figure out if they can give this person some fraction of $2,000, like $50 or $100, not to go. Why not? It's an investment well made. So we're just going to actually clean this data a little bit. We wanted to make these yeses up here into ones and the no's into zeros and stuff like that, and that's what's happening here. And we'll just randomly, actually, not quite randomly, but chose some columns over here to do this stuff. Okay, the first thing you should notice is that this is an extremely asymmetric data set. Most customers don't leave. Most customers are too lazy to leave. That includes me. I just stick with the company because, who's going to put in the effort? And so the people who churn are like about 14 to 15% of your customers. You want to reduce that number, obviously. That's the game you're trying to play. So they should actually tell you, so at this point the bell should be going off in your head, is that if I use accuracy as a metric out here, there's one classifier I could write, which is dumb and stupid, which actually does really well. And this is a classifier which predicts no customer leaves. And that classifier is right 86% of the time, right? Because 86% of the fellows don't leave. So you would say that maybe I actually have to beat this classifier. And you'd be wrong if you said that you have to beat this classifier, simply because that's really not the metric of importance over here. What's the metric of importance? Well, we'll come to that in a second. So here I'm going to reproduce the confusion matrix over here. And to show you that accuracy is kind of like a bad metric to use in this particular situation, here's this diagram also taken from Fawcett's book, which the ROC diagrams are taken from, which kind of illustrates two different classifiers. There's a classifier A and a classifier B with this churn problem. And the way the classifier A makes mistakes is by having false positives, right? These are people who won't churn. This is the observed stuff. These are my predictions, but who I predicted to churn. So it makes these false positive errors. The way classifier B works is that it says it makes all its mistakes as false negatives. These are people who will churn, but who I predict not to churn. And I train these classifiers on a balanced set of people who churn and who don't churn, which is not true in real life, but sometimes you have to do that. In fact, SVMs typically you need to train on balanced sets because they don't do very well otherwise. So now, in real life, when I go to my test set, I have a completely imbalanced test set. Most people don't churn. Here's an example where 90% don't churn and 10% churn. What happens? Because this part got expanded so much, right? This becomes much bigger. And at this point, that part got squished. So this becomes much smaller. And you're going to say, hey, we won. A is not such a good classifier. B is a much better classifier. You can see that little error thing out there is really small. And we can go home because B is a good classifier. Because B is a classifier. Okay. But here, again, that whole cancer thing raises its head. Or in this case, the telecom thing raises its head. Think about the relative costs of false positive and false negatives here. Okay? What's a false negative? So the false negative is a person who would have left our company, but who we predicted would not leave our company. So we lost that $2,000 in the next 3 years from them. False positives, on the other hand, are people who are not going to lose our not going to leave our company, but we think are going to leave our company. So we actually give them this, we send them this thing. It costs us $3 to mail it out to them, and it costs us, $100 of a discount we give them. So it costs us $103. Now, depending upon the relative ratio of these two things, one or the other could be actually particularly important. So even if this is like, maybe 100 customers, and for 100 customers I'm losing $2,000, that's a lot of money I've just lost over there. This might be 1,000 customers, or 1,000 customers, I'm spending $100 each. That's much less. So depending upon what these values of the money I spend on them are, one or the other of this could be different. Typically in these kind of situations, the cost is so, 10 minutes? The cost is so out of whack, right? I mean, the cost of losing a customer is so much more, or the cost of having cancer is so much more than not having cancer, that your false negatives tend to be way, way, way more expensive. And classifier B, which looks like the better classifier over here, just because on this diagram, just because it has a smaller red area, actually is not the better classifier. You're okay with making false positive errors. You're okay sending $100 out or $50 out or whatever, whatever your offer is. Again, now if you made an offer of $1,000 per customer, yeah, that may be different. So that's part of the business decision thinking that you have to do in this scenario. So if you're working for a company or if you're working for a doctor in the medical field, classifiers should be about the business end. And that is keeping, well, so it's just kind of like a stupid pun out there, keeping costs down for your business. But it could be killing less people if you're a doctor. Well, killing no people if you're a doctor, but you get my point. So you should always establish baseline classifiers first when you do any of this stuff via profit or loss over here. And since we'll stop talking about the cancer problem right now and just think about this from the perspective of this telecom company which is losing these customers. We should see what the costs of the situation are. So let's actually write down these costs. And we write them down in a cost matrix. And the minus of that is the profit matrix or the utility matrix, and you'll be using that in your homework instead. And that, in this kind of matrix basically has exactly the same form as the confusion matrix. But instead, the numbers in here are the costs of the various scenarios. So out there you get a true negative cost, true positive cost, false positive cost, false negative cost. What are these costs? Here, let's see. True negatives are people we predicted not to churn, and they won't churn. We don't have to spend any money. We predicted they won't churn. We're not going to send them a mailing. We're not going to make them a $100 offer. That's 0. That's this number here. Okay. False positives are people we predicted to churn, and these guys won't churn. They won't go away. We've wasted $3 on sending them the mailing, and we've wasted and in administrative costs and all that kind of stuff. And we wasted $100 because they're like, oh yeah, this is a nice telecom company. They're just giving us this $100 off our bill. We'll take it. So they take the $100. False positives. These are people we predicted won't churn, so we didn't send them anything, but we lost them. So from this way, we have to figure out what their lifetime value is and put that as a false negative cost. So say here I made it 1,000. We could have said 2,000 over 2 years. Typically, for these telecom churn scenarios, it works out to between about $40 and $50 per month per customer. So you can do the math as to what that number comes out to be. The true positives, these are people who we predict will churn, and they will leave us. So we're like, okay, these are the people we do need to make offers to, right? And these are the people that we can do something with because we know them to be positives. We know, they're people who will leave, who will leave us. We may try and actually get them back. So we make them an offer. And let's say F, say we're going to leave and go to Verizon anyway, in so a fraction F. Then 1 minus F fraction remain with us. So basically the cost of this is going to be F times the offer cost plus, sorry, so F is the fraction that leave us actually. Or I think maybe I had that wrong. The F is a fraction that leave us. No, it's the other way around. F is the fraction that stay with us. So F is the fraction that stay with us, and then that's the offer cost because they would have stayed with us. And then 1 minus F is the fraction of people who would leave us. And then we've lost their lifetime value, and we've had this administration cost of sending this stuff out to them. And so let's just assume this kind of fractional value is something like 0.5, just for the sake of this. And as a business, you should sort of get an idea what this number is. And actually calculate this cost matrix for us. And so here's the cost matrix. The true negatives are 100. The false positives, the true positives are 551. The false positives are just costing us $103. And the false negatives are 10 times as expensive. They're costing us $1,000. 5 minutes, okay. So now, to actually calculate the cost, I can just calculate an average cost per person based on a very simple formula. You can prove this formula, and we'll probably show you a proof right at the end of the semester on how to do this. But you can prove, but this is kind of intuitive. It's basically saying it's the cost of a false positive times the odds of a false positive plus the cost of a false negative times the odds of a false negative plus the cost times the odds of the other two, divided by the total number of people we have, because the number of false positives, sorry, just the odds over here, but in this next slide, it's just saying the number of true positives divided by the total number of people. That's an estimate of the probability. So this is not necessarily an accurate estimate, right? Because we don't actually know the real probability distributions over here. But we can estimate these probability distributions from what we got in our confusion matrix. So that's what we're doing over here. And those are those numbers that come directly out of the confusion matrix, and we're dividing by n. So this is really a simple formula to put into Python code. Basically, you make the confusion matrix between your actual y and your predicted y, and you basically just sum up the product of those two matrices, the confusion matrix and the cost matrix, and you divide by the total size, and you return that score. So now what we do is we do the same thing we did in the previous notebook, where we basically did the strain test split using these indices and everything amongst people who churn, and churn mask over here between, sorry, I said that wrongly, between a training set and a test set. And on our test set now, we just look at this. We say, okay, let's create a situation where we have this model which we call DTSE or DSTE over here, which is, well, what I'm saying, don't send to everyone, which means this is the one where nobody churns. I don't send anything to anybody. And in this particular model, basically I'm saying everybody's a 0. That's my prediction, right? And p dot zeros of the test size. And given that prediction, I can get the confusion matrix, and it looks like this, and I can calculate the average cost, right? These were the y's on the test set, basically. That's the prediction, all zeros, and I can put in the cost out there, and it costs me $141 per customer, not to send anything to any customer. Okay? There's the assumption which I can make, which is a completely other assumption, which is that everybody is going to leave me help, right? And this is the thing where everybody is a 1. The prediction is that everybody is a 1 over here. And I can get the confusion matrix, and that's what it looks like. And I can calculate the average cost, and it's more. That's not surprising that it's more per customer, right? Because you're assuming that everybody's going to leave you. So then the cost for having to deal with that is going to be more. So obviously, the first one is the one to beat, right? That's the one which says that those remaining 15% who that nobody churns. We've sort of like misclassified this 15%. But the cost of that is 141, and we need to do better than the 141. So I think I'll stop here, and next time go on to how to actually deal with this in the context of classifiers themselves. Yeah. Okay.